All right, folks, our last little bit that we're going to do in prop day, we're so close to being done, is some reasoning about nat sets. So here we're going to use the list-based sets of naturals, in particular the ones that it's just the no duplicate ones, not the sorted ones. We'll reason about sorting in tomorrow's work in day 17. So what do we have here? So first we redefine a couple of operations that we had you define, just because we want to make sure you're using the definitions that we know are easy to prove things about. There are of course other definitions, but these are the ones that we know how to do the proofs for really well. Okay, so take a look at these if your solutions were different, not a big deal. The the thing I really want to show you is here is an inductive predicate, an inductive proposition, excuse me, characterizing those lists of naturals, nat sets, that are actually sets of naturals. So set like nil says, hey, the empty list is a set of naturals, it's the empty set. Set like con says, okay, you give me an x and an l that's a nat set. And if x is not in xl, so in is this thing we defined in day 15, right? This fixed point programming with propositions thing. And if L is itself set like, that is, there's no duplicates, then x cons L is set like. Right? So this is reflecting the sort of idea we see here, like if it's not anywhere else in the list and the list is set like, then the whole thing is set like. Okay, so there's some exercises here to get you going with this. The first thing is just playing with this, making sure you understand the relation well. Just, things that are set like, things that are not set like. And then there's some equivalences, right? So these are just various things that are important to understand about sets, various properties we want. This one doesn't talk about set like at all, but other things we might want to say reflect is set like. Slightly adjusted my window. Reflect is set like. We might say, for example, this is a common kind of proof that, hey, if a list is set like and we call set insert on it, then it's still set like. Um, if we have two things that are set like and we take their union, that'll also be set like. Right? This preservation property is how we can become confident that our definitions are sort of doing the right thing with sets. Okay, so these I think are all not so bad. This one is optional. These two are not. And then at the end, for those of you who feel like you want some challenge or just want to try something interesting, I'd like you to prove a complicated set identity lemma that's union distribution over intersection. The intersection of union L1, L2 with L3 is the same as taking the union of L1 intersection L3 and L2 intersection L3. Okay, so you can do this proof. You are actually going to need these set-like assumptions to get it to work. You're also going to need several helper functions because, for example, you'll need to know how intersection behaves, not just how union behaves, and so on. Sort of there's a bunch to do here. That's why this one is 4 stars and optional. So no pressure. Could just be something good to do. Thinking about it is, I think, a great exercise in any case. Okay, that is it for today. We did it. After this, we'll just be applying our hard-won knowledge to various case studies, various interesting programs we've written so far. All right, talk to y'all soon.